So, ladies and gentlemen, welcome to today's talk on Nexmon. It's our firmware reverse engineering and patching framework. It allows you to write firmware patches in C for firmwares running on your Wi-Fi chip, for example, on your smartphone. So, who of you already tried to maybe monitor or inject raw frames, Wi-Fi frames with a smartphone? Who of you ever wanted to do this? At least two persons. Yeah, Nexmon might be the perfect solution for you. So the thing about Wi-Fi chips is the ones running on the phone, they are normally FullMAC Wi-Fi chips. And the firmware running there is proprietary, so you don't have access to change it. So I would say Wi-Fi chips are imprisoned as they are currently available on the phones. However, with Nexmon, we are trying to jailbreak those chips and create patches at first in assembly, but that was very tedious and error prone, and then we went to writing patches in C so that you can simply implement algorithms and everything in C and run it on your chip's firmware. In this talk I will give you a little presentation about the story of Nexmon, start with some related work, give you an insight in this chip architecture, then explain you how we extracted and analyzed and patched the firmware. Then I will explain you a bit about our evaluation of a ping offloading example application and give you some more examples for other Nexmon applications. So regarding related work, our first intention when we initiated the project was to get monitor mode and frame injection running on a Nexus 5 smartphone, therefore also the name Nexmon. There were two other projects also doing similar things on older devices like MonMob and BCMon. Those are the projects just activating some extra features in this FullMAC devices. But there are also other works that try to implement advanced Wi-Fi based applications in softMAC devices on the real-time processor on this phone. So they are normally built around this OpenFWWF firmware. It's an open source implementation of the firmware running on this real-time processor, and couple of works resulted from this, like location discovery or reactive jammer or wireless MAC processor and many other works. So what we try in Nexmon is first, of course, to activate monitor mode and frame injection on smartphones, even newer generations, and then also be able to get advanced Wi-Fi applications running on the firmwares of smartphones. And in the end, everything should be open source so that other researchers can benefit from it. So let me go on with the chip architecture. So every Broadcom chip is built up in the same way. There are only two differences. On the one hand, there are softMAC chips. On the other hand, there are FullMAC chips. All of them have some kind of a backplane bus. And in the end, there are a system on chip. So you have multiple cores connected to this backplane bus. In every chip, there is a physical layer to do the modulation and the analog front end. Then there's this D11 core, it's the real-time processor, scheduling timings for acknowledgement and everything that is real-time. And then there's the host interface. It can be PCI-Express, SDIO, or whatsoever. And this is connected with the softMAC driver. And in the softMAC driver, you normally do all the non-time critical MAC layer tasks, like producing Wi-Fi frames and passing them on to the D11 core for transmission, and then they will be transmitted by the physical layer. So the difference with FullMAC chips is that you have a driver that does not generate Wi-Fi frames and send them to the chip, but instead you only generate Ethernet frames and pass them on to the Wi-Fi chip. And in the Wi-Fi chip, there's an ARM controller running that actually has the same objectives as the softMAC driver for the softMAC cards. So when you try to transmit a frame, you generate an Ethernet frame, pass it to this ARM microcontroller, that will be converted into a Wi-Fi frame and passed to the D11 core for transmission. One other thing we should look at is, as we want to modify the firmware, we should understand how it is loaded. Using the softMAC driver, you can only load the firmware for the D11 core. If you want to load the firmware on the FullMAC driver, you normally only load the firmware for the ARM processor. But in this firmware is the D11 core firmware embedded. So after loading the ARM firmware in an initialization phase, the D11 firmware will be loaded into the D11 core, and that means with our Nexmon framework you will be able to modify both firmwares for the D11 core and the ARM core and run whatever applications you want on the chip. The next thing is that for analyzing the firmware, you should have the whole firmware binaries to be able to analyze all parts of it. Problem here is the ARM firmware is split in two parts. One part is loaded in RAM. That is the part loaded by the driver, and then there's also ROM, which comes directly delivered with the chip. It's read-only memory, so you cannot actually change it, but there's part of the firmware inside. So we first need to extract this firmware here, and having both parts of the firmware, we can put them together, merge them in one firmware file, load it in IDAR, and then analyze the firmware source code. Normally it's just assembly. You can decompile it, then you have something C-like, but still you have to identify functions and so on. So how do you do this? Fortunately, on the Broadcom devices, it's quite nice because they have some debug messages inside. So here, for example, you can find a format string, and here you can find actually the function name where this debug message was generated, and thereby you know the function name of the function that was calling the debug message. And you can guess that the function called afterwards will be a printf function. So that is not the only source for finding out what's going on in the firmware. There's also this BRCM SMAC driver. It's an open source driver for softmat cards, which has very similar function names so that you can reference them and find out what functions are in the firmware. Then we also used some other sources like leaked WL driver source codes, or we looked into proprietary combined source codes, for example for macOS, as they contain symbols, and there you know how the different functions are called and which functions call which other functions. So let me go on with the firmware patching. As I told you before, we first started by writing assembler source code, assembling it into some binary files, then using some crappy Python scripts to patch them into the firmware, and then decided that's not the way to do this firmware patching, as it is very tedious to write assembly and it's also error prone. So we continued to create a framework that can compile C files and embed them in the firmware. So everything that goes in the firmware is just saved in the C file. When you compile it, you get object files, and during compilation we run our Nexmon GCC plugin. It can extract some additional attributes we can put in the C source code and write them in another text file that we can then use for linking and other things. So how does this source code look like? Let's go back to our example here where we have this printf function printing out a debugging message, and we would like to replace this printf function and call our own function. So you can see there's a branch link instruction here that we would like to patch. So in the patching framework we have a couple of C macros that can be called, like the BL patch. You can give it a name so that you can find it later on in the files, and you can say which function you want to call with it. And then we would have to define the address at which this patch should be placed in the firmware, and this would be just at this given address here. I told you before that it's a bit hard to handle the read-only memory because you cannot actually write to it, but there's a flash patching unit that lets you override some parts of the ROM during runtime, and you can simply activate it by writing flash patch here at the attribute to implement such a patch. So let's go on with the patching framework. From this nexmon.pre file we create linker files that tell the linker where to place the different symbols from the object files, and we create make files. The linker in the end creates an ELF file, and the make files are used to extract sections from the ELF file and integrate them in the original firmware together with the patched firmware. In the end you just run make and everything is done for you, so you do not need to care about anything else. Next thing is a patch placement. So far I only told you how to place a very simple function or a simple instruction at a certain address. But what happens to the functions that you actually want to call, like this target function that we have here? This has no specific address where it should be placed. So we simply decided we can collect all the functions that are not explicitly placed in a certain region, and the linker will put it at a certain place where we want it to be. And therefore we developed this special pragma target region and told it to place everything that is not explicitly placed in the patch region. Now, where do we place the patch region? On the Nexus 5 we were very lucky because at the beginning of the firmware there's one part that is always free, there are always zeros inside. So at the beginning we just placed all those functions in this free part. But suddenly we were running out of space, and then we also wanted to move to other chips, and they didn't have this free part anymore. So we had to find another option. And as I told you before, the ARM firmware also includes the source or the binary of the D11 firmware. And one thing about this firmware is that the entropy is quite low, so that you can compress it very easily. So instead of roughly 40 kilobytes of firmware code, you can compress it by roughly 50%. And then free some more space that you can use for your patches. It has one downside that needs to be fixed, because generally after loading the D11 core firmware, the RAM part is freed and assigned to the heap so that it can be used for storing frames and other things. So what we need to take care of is to reduce the size that is freed so that our patch code is safe. So let me continue with an example application. I was thinking about something easy that I can implement for this paper to show you the benefits of implementing stuff in the firmware instead of running it in the Linux kernel on your smartphone. And I was thinking about a scenario with two devices. There's a device under test and a communication partner. The communication partner simply generates frames, sends them to the device under test. In the Wi-Fi frame, they will be converted into Ethernet frames, sent to Linux, and there they should be somehow processed. There should be another frame coming out, sent back to the Wi-Fi chip, and sent back to the communication partner. Can you think about any application that does exactly this? Like getting a frame and sending it back? Any idea? Ping. That's true. So instead of just implementing a new kernel module just for our application, we just said, yeah, let's use the ping application. So and what we intended to do to test how well it would work to simply implement the ping response in the firmware, we generate the frames again, send them to our Wi-Fi chip, but instead of passing them onto Linux, we process them here and send them back. So let's look at some results. Before we do this, we have to consider another point. It's a power measurement. We also wanted to measure the power used by just handling this ping application in the firmware or in the kernel. So we had to attach our phone to a power monitor. Unfortunately, if there's a battery in the phone may draw current from the battery and the power monitor. So first we had to remove the battery, then attach the power monitor, and thereby we could measure the power during the operation. So in the power consumption measurement, we were running our phones in ad hoc mode and then sending pings between them. And to simply run the Android device in ad hoc mode draws like 250 milliwatts all the time, because you always have to run your receiver. Then if we handle the pings in the firmware, you can see that if there are only a few pings, it doesn't really make a difference in power consumption. If you have a couple of hundred pings per second, the energy consumption increases as you have to spend more power on transmitting the frames. But if you handle the frames in the kernel, you will directly see that there's a high increase in energy consumption as soon as you turn on the main processor on your smartphone to handle the frames. So it's much more energy saving to simply do it in the firmware and let the main processor of your smartphone sleep all the time. Another thing you can see here is with an increasing number of pings per second, the energy consumption goes up, but at a certain number of pings per second, it just stays constant. So we were asking ourselves, how could this be? And therefore we analyzed another metric. It was the actual number of ping requests sent per second compared to the number of targeted ping requests we wanted to have. So we ran our ping application with, for example, 6 pings per second or with 1000 pings per second, but that doesn't tell you that so many pings really go through. So if we handle the frames in the kernel, you can see that at roughly 200 pings per second, there cannot be more pings handled anymore in the kernel. But if we handle the pings in the firmware, we can at least handle up to more than 500 pings. So your throughput is much higher when you process single frames. Of course, aggregation of frames was deactivated so that for every ping packet you actually send one Wi-Fi frame. So the next thing we analyzed is the round trip time. So that means we measure the time between transmitting a frame from one node to the other and waiting until the frame comes back to the transmitter. And here we can see that when handling the frames in the firmware, the handling time is always constant and it's quite low. So we always have a deterministic and low latency. But if you want to handle the frames in the kernel, it can take much more time to get an answer back. If you have a low number of frames being transmitted, your main processor might be in sleep state and might need to wake up for every frame that it receives. And only after a certain number of frames you will get some constant round trip times. So far for this example application for this paper. We also implemented some other applications based on Nexmon. For example, for the WiNTECH conference this year, it was a reactive smartphone-based jammer. So whenever you receive a Wi-Fi frame, you can analyze it in real time and then decide if you want to send out a jamming signal to destroy the frame while it is still being transmitted. And the jamming signal could even be an arbitrary waveform because we discovered that there is an IQ buffer in the Wi-Fi chip that you can fill with your own IQ samples and then send them out, so like with an SDR. Another application that we have on the Google Play Store is a penetration testing app, so you can run your phone in monitor mode and you can have an arrow dump view or Wireshark dissection of all the frames being transmitted. If you want to take a look at both of the two applications, I have a demo ready in the back. And something else which is upcoming is an accepted Conex paper where we ported a Nexmon to the first 802.11 AD devices that are commercially available, and also did some measurements there. The nice thing about all the works is that the source code is freely available, so everybody of you can use it and just run it on your phone. We even support one iPhone and a couple of Android smartphones and the Raspberry Pi 3 and 0W. And that's it from my side. Now feel free to ask questions.